So in order to make the obstacle avoidance program, we're going to need several helper functions. Most of these should be familiar to you because we created them in the motion control code. One of the new ones is going to be all LEDs off, which the LEDs are our state indicators. So this helper function goes through and loops through all 4 LEDs and turns them off. The next helper function is get distance, and it takes in 2 pointers, int X and int Y, which represent the trigger and the echo pins. So then we have the variables echo time, calculated distance, and the trigger pin and the echo pin. And we digital write the trigger pin high, wait for 10 microseconds, and then digital write the trigger pin low. And then we count the pulse ends as an echo time from the echo pin, and then we use that to calculate the distance by using echo time divided by 148. This returns the distance in centimeters. The other new helper function is random wander. So when the robot is not avoiding obstacles, it can either drive forward or it can random wander. The random wander function generates a random number by using the random function, and it uses that random number to generate a distance and an angle. That distance can be passed to the forward function for the robot to determine how long the robot moves forward. And it can also be used for a delay to determine how long the robot moves forward before shifting to a turn where the angle is also generated as a random number. Random wander can be written in several different ways. So this would be a place for you to show your creativity by changing how you generate the random number and what you use the random number for. So now that we've set our helper functions, let's go through our main program. The first variables that we've defined are our LEDs, our state LEDs, which will be connected to pins 4, 5, 6, and 7, where the red LED is on 5, the blue LED is on 6, the green LED is on 7, and the yellow LED is on 4. Then we define our trigger and echo pins for the sonar, where the trigger pins are at 2, A2, A0, and A4. The echo pins are at 3, A3, A1, and A5. And we're also going to have a state variable that will represent the presence of obstacles around the robot. We then have a global variable distance equals 0 for reading one of the sonar sensors. And we have a vector with 4 elements, dist of 4, that reads all 4 sonar sensors and holds the distance data there. For the motors to control the robot, and we discussed these when we did our motion control video, we have AN1, AN2, and PWA at 8, 9, 10. PWMB, bin 2, and bin 1 at 11, 12, and 13. And then robot behavior variables for moving. We have a move time, a robot speed, 1 second, 2 seconds, and a wait time. So now we have our setup function, and this is the code that will only run once. So we have one loop function that sets our LED pins as outputs. We have a loop function that sets our trigger pins as outputs. And we have a loop function that sets our echo pins as inputs. And then finally, we have warning LEDs that turn on to let us know that the robot will be moving, and we turn on each of the LED pins to high. Then we set the motor control pins as outputs. So we have AN1, AN2, PWMA as outputs, and bin 1, bin 2, PWMB as outputs. And then we define the baud rate for serial communication for debugging our robot as 9600. And we serial and begin the communication with the serial monitor. And then we print out Rosie-bot begin. Then we have a short wait time to give you time to get the robot on the floor so that you don't drive it off the table. And after that, the lights turn off. So now let's look at the loop function, which will run continuously. The first thing we're going to do is have a for loop that iterates from 0 to 3 that will read each of our distance sensors, front, back, left, and right. And then we will delay for 10 seconds, print out the distance data. And then we have if conditions that if the distance data is greater than 0 or less than 2, which indicates the presence of an obstacle, then the state variable for that respective sensor, whether front, back, left, or right, is set to 1. If there's not an obstacle within 2 inches, then that state variable will be set to low. Next, we print out the state variable front, back, left, and right as part of our debugging to determine when the states have been set so that we can then use our switch case to make a decision about how the robot should move based upon the presence of an obstacle. So if the switch state is case 1, which indicates a front obstacle, the serial monitor prints front obstacle and the robot backs up. If the switch case indicates state 2, that means there is a back obstacle and the robot drives forward. If the switch case is a left obstacle, the robot spins right. And if the switch case is an 8, which is a right obstacle, the robot spins left. If there are no obstacles, the robot sits still. So this is where there are opportunities to modify your code, because you could also add cases for multiple sensors being triggered to add more switch cases. And the default state for the robot could then change to either forward, so that the robot always drives forward unless an obstacle is detected, and then it will either spin, reverse, or move forward. Let's take a look. All right, Rosie-bot sensor test motion, not proportional yet, just straight bang bang on off. Eventually it'll be proportional, integrated with forward motion and random wanders.